Hello, friends. My name is Derek Carter, and in this lecture video, we're going to be looking at the basics of deep learning, so an introduction to the topic. These are a set of lecture videos for my 560 course on deep learning and neural networks. We are using this textbook. I highly recommend it, the Deep Learning of Python by Francois Chollet. Dr. Chollet is the original creator of the Keras framework. So this textbook is more geared towards the practical side rather than the theoretical side. It has as much stuff about understanding the Keras framework and TensorFlow in order to do deep learning as it does with what deep learning is and kind of the theoretical side of things. I wanted to give this is material basically based on the chapter one. It's just going to be an introduction to deep learning, so what it is, the basics of how it works, and things like that. Okay, so this is mostly material from chapter one from our textbook for this class. So first of all, deep learning is kind of a specialization of neural networks and machine learning, which they in of themselves are specializations of artificial intelligence. Okay, so if you don't know what artificial intelligence is, it's basically the basic idea of AI is it's the effort to automate intellectual tasks on a computer that would normally be performed by humans. Okay, so AI has been around for a long time, since the late 1960s. And there are some specializations of AI that are outside of what we're going to be doing in this course. So things like expert systems or rule-based systems or Bayesian networks, things like that are really AI and not kind of what I would think of as machine learning for this course. Okay, so machine learning looks at inputs and answers, and it tries to figure out the rules. Okay, so machine learning, I'll go into more details of this in a bit here, but it's really automating some of the stuff that a programmer would do to take inputs and the correct answers for those inputs and to determine the rules for those to build a system. Okay, so if you took my previous 574 course, a lot of the stuff is a good prerequisite for the things we'll talk about in this course, right? So deep learning and neural networks builds on the basics of linear regression and logistic regression sorts of systems for machine learning. Okay? So in this course, we're going to look at deep learning. So this deep learning is I could have added another circle here. It's really kind of a specialization of neural networks in general. So we're looking at both neural networks and deep learning in this course. So deep learning is where we're going to be learning successive layers of increasingly meaningful representation. Okay? So in classic machine learning, like a logistic regression, there's really only one central tensor transformation or affine transformation. So you just learn one transformation to go from the inputs to give your prediction for the outputs. So in deep learning, we'll have multiple layers of those, and we'll try and organize those as a hierarchical succession of increasingly more meaningful transformations or representations. Okay? And then finally, our course will get up to, but it's not mainly about generative AI. So generative AI or large language models, things like ChatGPT or the models for generating video or generating images are all examples of this type of generative AI. Okay, I do hope we'll talk a little bit about this at the end of this course here. So generative AI basically is using deep neural networks and extends those from reactive tasks. So in deep neural networks that we're going to be doing in this course, we're mostly going to be concerned with building things like classifiers, like we did in machine learning. So taking an image and classifying it. You know, is it an animal? Is it a vehicle? That type of thing. For generative AI, it's trying to be more what you generate, so to creative activities. That's kind of the main difference between classic deep learning and these new large language models. Okay. So a little review about machine learning. So this is the basics of how machine learning works. In in classic programming, the programmer will take the data and he knows what the correct answers need to be for the data that he has. So the programmer has to come up usually with the set of rules. So you write a program, like a C or Python program, that will process the data as inputs and give the correct answers. Right? So in machine learning, which is a type of artificial intelligence, the programmer is kind of taken out of the loop. So the learning in machine learning is that we're going to give the machine the data and we're going to give it the correct answers. This is a type of supervised learning. And we want the machine learning algorithm to come up with the rules that will transform the data into the correct answers, like we had before. Okay, so the machine learns the rules for us instead of us explicitly programming the rules. Okay. So in machine learning, to do machine learning, we need three basic things. We need the input data. We need examples of the expected output. So we need these correct answers to do supervised machine learning. And then we need a way to measure. Okay, so once we've learned a set of rules, the rules might be good, but they might be bad. So we need a way of measuring whether the algorithm is doing a good job or not. So this is going to be the loss function or the cost function that we'll use, right? And again, if you've taken a machine learning course, you should be familiar with these. So we need these even for basic machine learning where we're only doing a single transformation. But we need a loss or a cost function in order to guide setting up the parameters for any type of this supervised machine learning in order to come up with a good set of rules that works well to make good, accurate predictions. So a little bit more. So machine learning, some forms of machine learning and the forms that neural networks and deep learning are based on basically work like this. Okay, so you can think of having a set of raw data out here. So here we're kind of representing a set of data points, and we want to learn a task where this is a simple binary classification. We want to learn black classifications versus white classifications in the data set. Okay? So the way that a simple transformation like a logistic regression does, that you might have picked up in a machine learning course, is it actually creates a set of transformations to rotate and translate the data into a better representation. Okay, so we call those tensor transformations. We think of those in this class as a set of tensor transformations to take the original raw data and come up with a better representation. Right. So once you have a better representation, usually your rule becomes much easier, becomes trivial. So like in this case, the rule is that after these transformations, anything for the feature when x is greater than 0, we should classify as a black class. And anything for the feature where it's x, the parameter x is less than 0, we should classify as what? We should predict it's going to be in the white class. Okay? So that's the basic idea of what these sorts of a particular type of machine learning is doing. You can think of it as this sort of transformations, this coordinate changes in a high dimensional space in order to create better representations so that you can make finding or learning the rules easier. Okay? So for deep networks are a kind of neural network, but where instead of doing a simple single transformation, we do multiple transformations. So here in this figure from our textbook, we're taking the input, but we do several tensor transformations through 4 layers before we make a prediction for our output. Okay? So in neural networks in general, and especially in deep neural networks, we're interested in layered representation learning or also hierarchical representation. So one way to think about what's happening in a neural network that has multiple layers is that we are learning more sophisticated hierarchical representations of the data as we progress through the layers of a neural network like this. Okay? So like it says, information goes through successive filters and comes out increasingly purified through each of these successive layers as we're going through these transformations, and that ultimately should make it easier to make good, correct predictions on the final output layer. So deep learning is a multi-stage way to learn data representations for a complex input data task, input data transformation that you want to do. Right. So, a little bit more about understanding. So we're going to go into more details of this in subsequent lectures in this class here. So the goal for a neural network or a deep neural network is we have a representation that looks something like this. All right. So this is our first introduction to what a neural network looks like. So a neural network is really just a sequence of layers. So in this example, we've got two layers that are parameterized by a set of weights and biases. So each layer has its own set of parameters. We'll often call those, we'll differentiate into two kinds of parameters, weight parameters and bias parameters for our neural networks. Okay. So, but you can think of these layers as the same sorts of transformation. These are really just doing a linear regression or a logistic regression. So the transformation is something like a rotation or a translation or some other manipulation of the data from the input data space to the output data space. But for a neural network, we do that multiple times. So the output from layer 1 becomes the input for layer 2, right? And we can have many, many layers in a deep neural network for this, right? But the point is that all these layers are parameterized by the set of weights and biases. So we think of these as the parameters for each layer or the parameters overall for the neural network. So the key to machine learning is we need what's known as a loss function, or also called a cost function. Okay, so I'll use that term interchangeably, loss or cost function. So a loss function basically measures the quality of the network's output. Okay, and this has to be a little bit more sophisticated than simply the answer being correct or not. Right. So this has to give us a measure of, the answer is very good, but it also needs to tell us, it's kind of close, but it's not very good, or it's a very bad answer. So it needs to be, the cost function needs to give us a signal that's a range from really good. So usually really good is going to be a cost of 0 for this loss score, up to a very high. So a very high score means that it's bad. That the prediction was bad. It's not simply incorrect, but was very off. Right? So once you have this kind of a loss function, you can so this loss function takes the predictions of the network and the true targets for supervised learning, and it computes this distance score, or this loss score, which captures how well the network has done on a particular input. So once you have that, the fundamental trick in deep learning is this feedback signal. Okay, so this feedback signal is going to adjust to the weight so that the next time it sees that input, it will have a prediction that's better, that's closer to the true target, thus minimizing the loss function. All right. So this loss score here is used as a signal for an optimizer. We're going to be looking at an optimization technique called backpropagation. Backpropagation, which is the fundamental optimization algorithm that's used in order to be able to simultaneously update all of the weights in a deep network at the same time in order to lower the cost, in order to get these predictions closer to the true target so that we get a lower loss function every time the optimizer runs and updates these weights. Okay? So, so this is the training loop. So this has to happen multiple times. So in this training loop is repeated where we feed in the inputs, we calculate the loss function, we hand those to the optimizer. It's responsible for figuring out how to modify the weights to lower that loss, to lower the cost that we have. Okay, so I did want to mention one thing. The textbook briefly discusses the promises of AI. You can call me a kind of a skeptic for the current round of generative AI. So I just want students in this class to be aware of. There's been multiple cycles of boom bust in artificial intelligence. So AI, is relatively old. It goes all the way back to the late '60s. But there's been several cycles where people have overpromised things, and then those promises of what AI could do didn't manifest themselves. So then people lost interest in AI, the funding went away. So these were kind of known as AI winters that have happened. This happened more than once. And there's a lot of interest, a lot of buzz about generative AI and large language models right now. But there's definitely again a series of things being overpromised about what it can do. Right. So I study AI and deep networks. I do believe that these things are very useful. We can build things that are very useful tools for us to do things with. Okay, it's just that what can be done with generative AI right now is the things people are saying that can be done with it are way more than what's actually going to ultimately be done with large language models, what it's going to be useful for. Okay, so I do believe we'll probably have another bit of a bust, and see kind of interest go away this after a bit. So I highly recommend reading Dr. Melanie Mitchell's article on this for a reasoned kind of a view, a more skeptical view of generative AI and large language models and the current state of things here in 2025. So there's a link to this article in the references here for this presentation. I already mentioned that in this class we are going to be going more on the practical side. So we will be looking at learning Keras and Tensorflow. So I've picked that as the framework. This is an updated version of the figure from our textbook. So this is from the 2022 Kaggle survey. Okay. So you'll see that well, first of all, I kind of did want to mention one thing that was talked about in the textbook. There's at this point in 2025, it is still correct that there really are two sorts of problems. So there's more structured data problems, and for those, typically, what works best if you have very structured data is to use gradient boosted trees. So gradient boosted trees are a type of ensemble trees that if you took my machine learning course we got into, we didn't get all the way up to talking about gradient boosted trees. But those work really well when the data has more structure. So when you already have like a JSON set of data or some other machine readable human created set of structured data, right? But when you have unstructured data, like if you're trying to do image recognition or you're trying to do machine translation, so natural language is a lot less structured, a lot less messy, or trying to take an image and determine what the picture is, it's a cat, it's a dog, is a lot less structured than what we're talking about for this type of structured data. So for those, deep neural networks are the state of the art. Those work the best. And there's really kind of two frameworks right now. So Keras with TensorFlow or PyTorch with TensorFlow. I'm more familiar with Keras. I think Keras is still more popular than PyTorch, but you can kind of see that PyTorch has been gaining popularity a little bit. And Keras has maybe been going down a bit, but those are the two major deep neural network frameworks that you might run across. And we're going to look at Keras in this class. And then finally, so why deep learning? Why now? This is more of a question for originally when deep learning took off in around the mid 2010, 2015 or so. But at that time, there had been a little bit of a bottleneck. So people had been doing neural networks for 20 years, but they didn't perform very well until some breakthroughs were made that enabled deep learning to be possible. So basically, we need kind of three things for in order to do deep learning. We need better hardware than was available at the beginning of 2000 or 2010s. So it's specifically in 2025 here, GPUs and tensor processing units. So graphical processing units and tensor processing units have allowed to give really tremendous amounts of computation to be able to be done to build these sorts of hierarchical models. Okay? Besides that, though, you really need large data sets to make deep learning possible. Okay, so like our textbook mentions, if deep learning algorithms are the steam engine, then really the data is like the coal. If you think of the deep learning revolution as something like the industrial revolution here, right? So having large, big data sets makes deep learning possible. But then finally, I kind of hinted at, but there was kind of a bit of a bottleneck that some new algorithms were kind of discovered in the early to late 2000, 2010 that made deep learning possible. So the basic problem was that for a neural network, that feedback signal to do back propagation fades as the number of layers increased. So excuse me, back propagation wasn't very effective once you had more than 2 or 3 layers. But from new algorithms, and we'll get into some of these in this course here, but from these it kind of enabled to have that loss signal so it could be used for many levels, many more than 1 or 2 levels. So you can truly build deep neural networks that engage in hierarchical learning of things. Okay, so yeah, here's the references for that. The Kaggle survey and the Melanie Mitchell article if you're interested. But yeah, that's it for this lecture. I hope that was useful for you, and I will see you in the next lecture.